Hello, in this video we're going to show or illustrate actually several things. One is we're going to derive the moment generating function for a k degrees of freedom non-central chi-square distribution. In the process we're going to illustrate I'm going to call it the multivariate LOTUS concept. And LOTUS stands for the law of the unconscious statistician. And because of what we do, in a sense, we're proving that the non-central chi-square distribution is this. And I'll point out each of those as we get to them. If we let y be a normal distribution, mean mu I, variance 1, from 1 to k, the yi's are independent, and we let x equal the sum of these yi squares, then x is a non-central chi-square distribution with k degrees of freedom and non-centrality parameter lambda, which is equal to the sum of these mu I squares. Now this is the density, and really you can think of this as a chi-square distribution, and this is a Poisson, so it's a chi-square distribution with Poisson weights is how it's kind of referenced in the literature. But now we want to drive the moment generating function for this non-central chi-square. And you generically represent that as m of t. And so that's the expected value of e to the t, which is you plug in e to the t times f of x, integrated over all possible values of that, the domain, and that's it. So now let's do that. So here, since this is the density, and we're integrating over x, anything that's not an x will bring outside the integral sign. And so we have an x here, and of course this x. And then we combine the exponents into this. Now this is from here to here, I don't know, I do things a little bit slower. It probably took me 2 steps, but ultimately you combine them, you factor out an x, and you end up with this. So now our goal is to think about this as another density, because then integration becomes trivial. And if you look at this closely, it's a gamma distribution. So this is alpha, and this bottom piece would be beta in a gamma distribution. And so we know what that integrates to. So everything copies down. So this is gamma of alpha, and then beta raised to the alpha. That's what it integrates to. Now there's some cancelizations here. So this 2 to the k plus 2i over 2 cancels with this one. And then we're left with this. So this comes down, that comes down, the I comes down, cancel, 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 cancel. So the only thing left is this 1 minus 2t raised to this power. And this is it. And at this point, I'd probably stop there and just call this the moment generating function. But there's some interesting pieces here that kind of lends itself to this is probably a Taylor expansion of something, but we'll come back to that. So now to quickly review the multivariate normal distribution of y1 through yk, where the y's are independent and they each have their own mean mu I. This is the density. And so that's a k minus k over 2. E to the minus 1/2 times this sum. Okay, that's just an FYI. So now if we have, now we want to find the moment generating function for a non-central chi-square distribution. So we just proceed as normal. But this x, remember that was the sum of the yi squareds. So now this becomes a function of the y's. And so the law of the unconscious statistician, that's a video I have that illustrates this concept in simple terms, and then at the end we kind of prove it on a more theoretical basis. It says that if you have a function of these variables, then you can use the density or distribution of those variables. So since this is y1 through yk, we can use this multivariate normal density distribution in this integration. So this becomes, so this piece is this, and then we take it times this multivariate normal. So this is here, and then this comes out front. And I just write that as in vector form. So this should be d1, d2, d3, d up to dk, because that's how many times we have to integrate this. Now, we need to trick it into another distribution. Okay, so that's sort of the goal. And then so we combine these exponents. Now this is the sum of yi squareds, and so if we expand this, we'll get a sum of yi squareds. And so there's two of them, and we factor it out, we get this. Then we get 2 yi mu I, but we have to take it times this negative 1/2, and we get this. And then we get plus mu I squared, which is this piece. I take it out because ultimately we're going to take it out front because it doesn't live in the y world. Now here, when completing the square, I always like to have this, the coefficient in front of that as a 1 of the yi squared. So I factor out this piece, okay? And then ultimately, then I factor out, from this, I factor out a minus 1/2, but it's really this. And then I like to think about this by itself. But if you factor it out from this, you have to do the same. So that's where this coefficient comes out front. Then you divide by 2, then you square it, and then you add, subtract a well-chosen 0, and you get this. So this is the square, what we did here. This piece is, we just bring it out here. Where are we here? My video. Oh, this piece, that should be a minus 1. So then, so then we multiply by 1 here, and the square root of 2 pi raised to the k. So we do that to make this, we take out that, when we were perfect squaring it, we took it out front, which is this, and multiply by 1, and then that makes this a multivariate normal distribution. So the mean is this, and the common variance is this, they're independent. So this integrates to 1, and we're left with this piece here. So this is here, we can add the exponents and we get this. And then if we think of this sum of the mu I squareds as lambda, then this becomes this value. And actually, and this is what you see in the literature for a moment generating function for a non-central chi-squared. But if you remember what we got on the first page, using traditional way, they don't even look the same. So now we got to evaluate if they're the same. So this is a background, a Taylor series about 0 of e to the t. So if we take the derivatives, we get the same thing back, and so then the Taylor expansion about 0, or a Maclaurin series, is this. Then you can show, so this, when you evaluate it at 0, that's 1, so all these are little 1s. And if you evaluate it at lambda over 2 divided by 1 minus 2t, and so that you plug that in for all the t's, that it becomes this, and then squared and cubed and etc. This evaluated as 0 to 1. So you can write that generically as this sum, right? Well, now from star on the first page, this is what we ended up with. So now let's factor out things that are not indexed by I, which are these two, and we're left with this. But didn't we just show that is the Taylor expansion of e to the t with this plugged in? So this piece becomes this. Now you can add those t's and you get this. And that's what we derived when we used LOTUS in the multivariate normal. So this is the moment generating function for a non-central chi-squared k degrees of freedom. Now, here's something interesting. Because of the uniqueness theorem of chi-squareds, moment generating functions uniquely determine the density. Okay, so on our original one, we got this, and we use this density. Right? And then on the second approach, we got this. And so since those two moment generating functions are equal, that's kind of another little proof that this is indeed the density for a non-central chi-square distribution. Well, anyway, that's all I have for today. Hope you enjoyed that. I sure did. Like the video and subscribe so you don't miss the next one. Thanks. Bye.